Hi, this is Jayaraj. This paper proposes a novel data frame abstraction for constrained devices. Data frames organize data in a spreadsheet-like or a grid-like fashion, supporting flexible selection of rows, row ranges, projection of column ranges, slicing and so on, and applying functions on these slices and so on. And they are ubiquitous and very useful in statistical computing and machine learning, and present in almost all major such platforms like R, Python, Apache Spark, and so on. The objective of this paper is to bring data frames to low footprint devices. Then we have these constraints when we try to do that. We do not have any heap or dynamic allocation facility to track selection or projection or slicing information as we create this dynamically create these slices, data frame slices. And we need a strong memory safety guarantees, since memory errors can have disastrous consequences in embedded devices. And we also need zero cost abstraction. That is, we need to map data frames directly to memory addresses without incurring an abstraction overhead when we consider this really low footprint devices. So the paper proposes data frame as a zero cost memory safe abstraction for constrained devices. And we already discussed the constraints under which we are making this data frame proposal. And in the paper we show that this can be done with combination of three techniques. One is a static data frame type system on memory addresses. So type system is specified directly on memory addresses. And a subsumption relation that relates fragments with a whole. So we need a mechanism for relating data frame fragments with a whole, and we do that through this subsumption relation. And then in order to reason about the typing correctness, we use a specialized formal logic. We use a form of separation logic. Separation logic is very powerful and employed in reasoning about pointer programs in presence of concurrency and so on. Of course, we do not need its entire power, so we construct a very specialized and simple version of this logic to help us reason about data frame typing. Now, let's look at a few examples of what projection, slicing, and selection on low-level data frames look like. Now, given this data frame, that is a data frame with where each row contains a 16-bit integer followed by an 8-bit integer followed by a 32-bit integer and m rows at address 100. We may wish to use that address 100 to access the entire data frame, of course. But we may also wish to use address 100 to only access for example, this column vector. Let's say the first column contains temperature samples, and we may wish to only access only the temperature samples for a particular operation. Or we may wish to access only the first row at address 100. So using the address 100, we may want to access only the first row. Or we may want to access a slice of the grid, a subset of the rows with all the columns, or a subset of the rows and a projected slice of the grid. That is a subset of the rows and subset of the columns. So now, so we want our data frame typing to be able to infer these fragment types from the type of the entire data frame, and also go back and be able to infer from the fragment types the entire data frame type. So that is one of the objectives of the data frame type system that we develop. So here you can see a kind of a a formal way of specifying types. So for example, this column type is basically k elements where each element is a 16-bit integer. Similarly, this slice is k elements where each element is a tuple of 16-bit, 8-bit and 32-bit integers. Now the main, the primary type term that we use to specify data frame types has the form T, where T is element type. S is what we call the stride. Stride is the number of memory locations of a single row in the data frame, and N is the number of elements or number of rows. So data frame type has the form T, S is a stride or the row length, and N is the number of rows. So this is the basic data frame type term that we employ. And here, if you look at type systems in the familiar types systems in programming languages, what is new here is probably this stride term. And the assertion at a T asserts that data frame of type T exists at address A. So this is kind of a formal assertion that we use. Now, given this, so let us look at some examples of this kind of assertions. So given this data frame, let's say we have a data frame allocated and laid out like this at address 100. Each row contains 16-bit, 8-bit and 32-bit integers and m rows. So let us say we want to assert that at address 100 we have the first row. So we want to select the first row. So we can specify that in this form at 100. So this is a element type of the row, that is a tuple containing 16-bit, 8-bit and 32-bit integers with a stride of 7. The stride 7 comes from the fact that if we add the sizes of 16-bit, 8-bit and 32-bit integers, so we have 2 plus 1 plus 4, so we get 7. So 7 bytes, and the number of rows here is 1. And if we want to select multiple rows, then we can specify that number here. And if you project columns, then again at address 100 we have an element type of I16, so that is the type of the first column, and the stride is again 7, because after T0, the first element of column, the first column, after 7 bytes you will get the second element of the first column. So the stride is still 7, and then this is the number of elements of the column. And similarly we can assert the type of the entire grid at address 100. So these are all valid typing assertions. Now, in order to relate the entire data frame type with its fragment types, we have a number of subsumption rules defined in this paper, and we take one example and discuss here. So let us say that we have a data frame at address 100. We know that we have a data frame, a column which has an integer column, let's say a 4-byte integer column, 32-bit integer column, column vector with a stride of 10 bytes. That means, the 4 bytes are used by the integer and the rest 6 bytes are unspecified. So there could be some other data or no data here. Similarly, let's say at address 104 we have a floating point column vector with element type floating point values. Again, these 4 bytes are specified as floating point values and rest of the 6 bytes are unspecified. So the stride here is again 10 bytes. So given these two assertions, we can make an assertion for a combined data frame that at address 100 we have a data frame with element type being pair of integer and floating point values. So these two are combined with stride 10 bytes. So the 8 bytes are occupied by this pair and the 2 bytes are again unspecified. And this is formalized using this inference rule. And in order to allow some dynamic restructuring of data frames, let's say we may want to first of all allocate, deallocate, reuse data frame memory, maybe free and reallocate a portion of the data frame and so on, delete a column, allocate a column and so on. But at the same time, we want to ensure that we have static memory safety and no runtime overheads. So we have a mechanism by which we can statically check the correctness of allocation and free and reallocation and so on. So now let us say at address 100, we have an unallocated sequence of bytes. Then we execute the allocation operation. So here you can see that we have to actually specify the address at which we are allocating. So allocation is only assigning a data type to an address. So we are not really allocating raw memory here. So here means that we are assigning a data frame type to the memory location 100. So we are saying we want to allocate at address 100 a data frame of type. This is a data frame type. So the element type is a pair of integers. Stride is 8 because each integer has 4 bytes, and number of elements, number of rows is 10. So if you allocate at address 100 this data frame, then we get this data frame allocated or at that address 100. Now after some computations, we may wish to free only the let's say only the second column, this column. So we specify the free operation. So we want to free the data frame, kind of a data subframe containing element type U32 with stride 8 and number of elements 10 at address 104. And 104 is the starting address of the first element of column, second column, that is U0. So once we execute this, the first column is untouched, but the second column, all the elements are now deallocated, and we have unallocated bytes available there. And then now we can allocate this something else, some other data type, a subframe in the second, where the second column used to be. So for example, we can allocate a floating point vector with stride 8 and 10 rows at 104. Now, so if we do that, we get a new data frame. Now we have replaced the first, the second column containing unsigned integers with the second column having floating point values. So this way we can delete and reallocate individual columns. Now, how do we reason about data frame typing correctness? First of all, we need a formal logical language for typing assertions, and we employ a very precise and a concise logical language based on separation logic. So the primary syntax is basically specified here. So the formulae, empty means it's an empty data frame. Here we are asserting that at address A we have data frame of type T. Here we are asserting that, so this star is called a separating conjunction. So it means that at two non-overlapping areas of memory, assertion P and Q holds. So for example, we could have a data frame assertion at one area of memory, and at a non-overlapping area of memory we have another data frame assertion. So that is what this separating conjunction means. And what is the precise mathematical meaning of let's say a statement like at A we have something of type, a data frame of type T. So since we have a logical language, we need a rigorous way of interpreting the statements in the language. So we give this interpretation or semantics by mapping addresses to primitive data type names. So the meaning of a statement like this, if we say that address 100, we have a data frame of with this tuple element type stride 7 and m rows. The meaning of this is that we have an abstract heap where memory locations are labeled with primitive data type names. So a valid heap for this assertion would be at address 100 we have I16, which is the first column data type. Address 101, it is undefined because this I16 can only be accessed using the address 100. We cannot use address 101 to access it. So at 102 we have I8, 103 we have the third column, and again 103 is the address to access that value. The rest of the memory locations containing the value, we have undefined type. It may contain the value, but the type is undefined. So it's an abstract heap. We are not holding, this heap does not hold values, it only holds type names. 107 is where the next row starts. Again we have I16 and so on. So this is how we give a formal interpretation for this logical language. And we have the separating conjunction where we say that P and Q holds for two separate non-overlapping areas of memory. When we say non-overlapping, this need not be non-contiguous. Like for example here, we have data frame assertion say that address 100, we have this data frame where the column type is I16 and I8 with stride of 7, which means that the last 4 bytes are unspecified. So so this is a heap which satisfies this assertion. So here these 4 memory locations, the type is not specified. Similarly, we have let's say we have another assertion where we say at 103 we have a 32-bit or 4-byte integer with stride 7. So we are only specifying the type for this memory location, and this, as you can see, these two are non-overlapping. So we are not, there is no conflicting or overlapping type assignments. Then we can combine these two heaps, and this combined heap satisfies this assertion that two non-overlapping areas of heap, these two assertions hold. So this is separating conjunction. And then we also have rules for merging these two assertions in case they are part of a consistent data frame. So we can combine them and create a simpler data frame type representation like this. So we can split and merge. And we specify a few generic data frame operations on which we can verify type correctness. So we have alloc. So alloc to A means we want to allocate at address A data frame of type to. Free to A means we want to free the data frame of type to which is present at address A. So if there is no data frame of type 2 at address A, then this free will it will fail the type checking. Similarly, 0 and 0 is for initialization, transform is for applying transformation functions on elements of a data frame. Now we can use Hoare logic style rules for verifying typing correctness. Now in Hoare logic, we specify the rules as triples. We have a precondition, then a program schema or a program fragment, and then a postcondition. The meaning is that if the precondition holds before the program executes, and if you execute the program, then the postcondition would hold. Of course, these are specified, so there is an implicit universal quantification here for all programs, or instances of programs. So we are not giving this rule specifically for a single instance of a program. So here the first rule is for allocation. This means that if we have an unallocated sequence of bytes at address A, so we have an unallocated sequence of size tau of at address A, and if I attempt to allocate data frame of type tau, then we get data frame allocated at address A of type tau. Similarly, if you have data frame allocated at address A of type tau, and if we free the data frame, then we get back the unallocated bytes. And similarly, we have rules for other operations as well. So here we have shown that through these three mechanisms: a static data frame type system on memory addresses, a subsumption relation that relates fragment types to the type of the whole, and a specialized separation logic for reasoning about data frame typing correctness, we can have data frame as zero-cost memory safe abstractions in constrained devices. Thank you.